Take a look at this word. No matter where you see it written down, the letters appear in the exact same order. If you're looking at a clock, you automatically read it as minute, a block of 60 seconds. But if you're in an office, someone might ask you to take the minutes, the formal notes that record what happened during a meeting. If a scientist describes a crystal under a microscope, the pronunciation shifts to minute, describing something on an entirely different scale. You don't have to pause to pick the right version. Your brain selects the correct definition naturally because it understands the situation the word is in. We see this same pattern in mathematics. A symbol might look the same every time we see it, but its job changes depending on its environment. Let's start in a familiar environment, a school math classroom. If a teacher writes 15% of 200 on the board, what are they really asking for? This text shows us the standard definition. The percent symbol translates literally to per 100, so 15% is an instruction to take 15 out of every 100 units you have. We view 200 as two separate blocks of 100. Following the instruction, we take 15 units from the first block and 15 from the second. Combining those groups, we get 30. We found the answer using the symbol's literal meaning. In this classroom setting, the percent sign is a tool for slicing a whole number into predictable fractions. But look what happens when we move from a classroom to a computer screen. In a programming language, you might see the expression 200, percent sign, 15. If you read this as 200% of 15, the math won't make sense. As this warning shows, coders use this symbol as a remainder command. It has a specific job, finding what's left over after division. Divide the first number by the second. Imagine a 200-unit container. We stack 13 blocks of 15 inside, reaching 195. The command looks for the leftover gap at the top. That gap is 5, so 200% 15 equals 5. Does the rule hold up if we reverse the numbers? Let's try 15 percent sign 200. We try to fit a group of 200 into a space that only holds 15. It doesn't fit at all, not even once. That means the entire block of 15 is left over. The answer is 15. In this environment, the symbol has a completely different identity. It isn't looking for fractions, it's a scanner searching for leftovers. When we compare these side by side, we see the proof. The exact same numbers and the exact same symbol can lead to two different answers, depending on whether you are at a desk or at a keyboard. This happens with other symbols too. Think about the letter X. To a writer, it's a letter. To a student learning multiplication, it's a command to multiply. But in an algebra equation, it represents a mystery number that needs to be solved. Even the asterisk changes. A mathematician uses it for multiplication, but a computer user might use it to search for every file in a folder. These symbols don't have one permanent meaning. They wait for us to give them meaning based on where we put them. There is no automatic logic built into these marks. They don't speak for themselves. As this summary reminds us, the first step to solving any problem is identifying the context. We have to know if we are in a classroom or a server room before we start. Getting the numbers right is only half the work. To be truly successful in math, we have to start by being careful readers.